the last class we already introduced what is the torsional vibration. We considered some simple cases of rotors like single degree of freedom system, 2 degree of freedom system, and also we extended the method for multi degree of freedom system using transverse matrix method. And then we also indicated in the last lecture that there is another method which is called finite element method, which is very popular and powerful, especially it can be applied to any general rotor system that today we will be studying. And as compared to the transfer matrix method, this particular method is having one small disadvantage in the sense that when the system degree of freedoms are more, then the matrices which we have to handle they become larger and larger. But with the present computing power, I think that should not be a concern to us. So today I will be explaining finite element method for torsional vibration. I will be giving some basic steps also, so that the formulation part of the especially developing the elemental matrices is clear to us. In the previous lectures we have already covered how to obtain the equation of motion for the continuous system for torsional case, and we ended up with a partial differential equation for such systems. So I will not be covering that part here. So directly we will be going for the solution of those equations through finite element method. Apart from that, we will be covering another kind of element, that is the gear element, and once we will develop the gear element, then through examples we will demonstrate the finite element method, so that the basic concepts are clear. I am explaining with the help of a simple diagram what is the continuous system and what is the equation of motion, which we already developed earlier. So this is the x axis of the rod and this is the z axis, and it is loaded with a distributed moment which is function of spatial coordinate, also the time. And at any general location of the rod, the angular displacement is taking place, that is x t. And if you see the side view of this rod, we can able to point out one point, that is, let us say, point P. The location of that is, let us say, x, y, z, and if you want to see the motion of that particular point P in a large view, point P is here on to the shaft, the radial position of that is r, and once it is getting displaced, it is reaching the point P prime, and this angle we call it theta. So here we are assuming that the point P is moving in a same plane, is not going toward the axial direction. Now the equation of motion for this kind of continuous system in which the stiffness and mass are distributed can be written like this. This is the density, this is a polar moment of area, and this theta is the angular displacement, t is the time, g is the modulus of rigidity, and this is the spatial partial derivative. So this is the equation of motion for partial differential equation, which we already derived earlier. Apart from this, boundary conditions are there, that is at ends of the shaft, So in this you can see this particular quantity is nothing but torque, and this is the angular displacement. Through strength of material formula, we know that T by J is equal to G theta by L. So this you can able to see that T is equal to G theta G L. So this is identical to this particular term, and that's why we are calling this as a torque. Now we'll be solving this partial differential equation with the help of finite element method. So in the finite element method, we assume the solution in a polynomial form. So this is the solution of one particular element which we assume in a polynomial form. Let us consider one element of the beam in which we have node 1 and 2, and this, let us say, element 1. So corresponding to this node 1 we can have displacement theta 1, and corresponding to node 2 we can have displacement theta 2, and the reference axis, that is a local coordinate system axis, can be chosen from left hand side of the element. In this particular element, maybe we can have moments also, that is also distributed. These are the external loads on the beam element. This particular solution which we have assumed can be written in a more general form like this. Where this vector contain angular displacements at various nodes of the element, which again we can able to write in more compact form like this. Theta here is time dependent and n is spatial coordinate dependent. This is called shape functions or interpolation function. Okay. Once we have assumed the solution in a polynomial form, we will substitute this solution in the equation of motion. So obviously, because this solution is approximate in nature, we will not able to satisfy the equation completely, so we will get some residue. So let us write the residue. Here theta we are writing with subscript or superscript E, that represent for the element, and this is the external torque which is acting on the element. So this is the residual, and here we will be using Galerichan method of the to minimize this particular residue, and we will be using shape functions as a weight function to minimize this residual over the whole length of the beam. L is the length of the beam. So we will be substituting this here. I am showing these steps so that the concepts are more clear. Okay. Here you can see that especially the derivative with respect to x of the theta, that angular displacement, is 2. So, we would like to reduce this, because by reducing this we can able to choose lesser degree polynomial as our solution. So, now we will be reducing this differentiation with by integration by parts. So, here the first term remains the same, there is no change in the first term. Second term, I am writing as it is at present. In next step we will be doing the integration by parts, and the third term, it remains as it is. Okay. So, here we will be doing the integration by part. This will be taking as first term, this will be taking as second term. So, let us do that integration. So, here first term will remain as it is, then integration of the second term 0 to h, h is the element length, plus g j. Here we are doing the integration differentiation of the first term, and then this integration of the first term, and this, and the last term remains the same. Here you can see that I we have attached to the this shape function, and they can have values up to r, that will be deciding what should be the r can be a integer number. In this particular equation, in which we could able to reduce the order of differentiation of x, you can see that now the maximum order of differentiation in this whole integral, and other terms are order of differentiation with respect to x is 1. So, that means according to finite element method we require completeness of theta and its derivative with respect to x. So, that means we will be requiring completeness requirement of theta and del theta by del x. And if we see, go back to the previous integral equation, inside the integral the derivative of x is also x here. Okay. So, we require the compatibility condition of one order less, that means up to theta will be requiring the compatibility condition. Okay. So, now we have seen the compatibility condition. So, what we can do, we can come back to the element here, and because we require compatibility up to the first derivative. So, at each node we can assign one variable, that is theta 1 and theta 2, this for element 1. So, if we choose the solution, that is x t, is a linear function, that is a plus b x. So, this particular solution will satisfy our requirement of completeness and compatibility condition both, and will be if we see the boundary conditions of the element. Here we have two boundary conditions. One is at x is equal to 0, that means because x axis is here, theta is theta 1, and x is equal to h is the length of the element, theta is theta 2. So, here we have two boundary conditions. So, that means we can able to obtain two constants in the polynomial. So, that is also satisfying our requirement. So, if we substitute these two boundary conditions, we can get these relations. Second boundary condition, a plus bh. Now, this equation can be solved for a and b. A is directly we can get theta 1, and b is nothing but theta 2 minus theta 1 by h. Now, we can substitute this in the previous equation. So, theta 1 plus theta 2 minus theta 1 by h into theta. So, this can be rearranged as 1 minus x by h theta 1 plus x by h theta 2, and this we can able to write in a matrix vector form like this. This is a row vector and this is column vector, and this is our standard form of the solution which we wrote earlier also, like this. So, these nx, n1x, nx, n2x are nothing but shape functions. So, this we can write in more compact form like this. So, here you can see that shape function is function of x, and the nodal displacements are function of time. So, this solution which we obtain will be substituting in this particular equation which we obtained earlier. We can have the r as 2 here. So, we can have two such equations here. So, we can able to combine them. So, let us combine them. So, combined form of the previous equation is this. So, we have combined here two equations, that is because this is a vector n1 and n2 is there. Then second term, here we are writing n prime represent the derivative with respect to x, and this, and other term which are not integral terms we are keeping in the right hand side. So, I am expanding that term. Second term is, so here you can see that n1 and n2 two equations we have combined here in one, plus the external momentum now we will be substituting the solution theta xt is equal to nx theta, that is time dependent. We will call this as nodal displacement, and represent the nodal displacement of the element. This particular solution will be substituting in above equation. So, we will get here we have taken out the theta double dot ne, which is independent of x, so we have taken out from the this integral. Then we have n prime represent derivative with respect to x. This is row, and this is a row vector, this is a column vector, is equal to, here we are substituting the value of x is equal to 0. So you can see that the x value of x is equal to 0, n1 becomes 1 and n2 becomes 0. So we'll be left with this particular term. Then here minus will be coming. In the next term we will be left with this particular term, because here h at x is equal to h, n1 is 0 and n2 is 1. So we will be left with this particular term, plus we will be having the terms corresponding to the external moment. All integrals are from 0 to h. This is the element length. Now what will be assigning this particular term, we will call it as a M matrix, that is a mass matrix. This particular term we will be calling as a K matrix, that is stiffness matrix. So equation can be written in a more compact form like this. These are for the element, so let us call it with the superscript E is equal to, now you can see that we can able to write this in more compact form by putting theta prime, which represent the derivative with respect to x, and the forcing term. Forcing term is something like this in the expanded form. So if we know the distribution of m, we can able to integrate this over the element. Next we will be obtaining the exact form of the mass matrix and the stiffness matrix. So mass matrix, as we defined earlier, is 0 to h rho j n vector and rho vector into x. So this will be rho j, if we multiply these two, we will get n1 square, n1, n2, n1, n2, n2 square dx. Because element is uniform, so rho and j can be considered as constant, so they can come out. So if we integrate this, we will get as a mass matrix of a one element. Similarly, we can able to obtain the stiffness matrix. Here n prime vector and these two vectors are there. So if we multiply them, we will get n1 prime whole square, n1 prime, n2 prime, n2 prime, n1 prime, n2 prime whole square dx. We have n1 as 1 by x by h, so n1 prime will be minus 1 by h. Similarly, n2 we have x by h, so n2 prime will be 1 by h. So you can see that this particular matrix is a constant. So the stiffness matrix becomes this. So this is the stiffness matrix for the torsional vibration. So now we have already obtained the equation of motion for one particular element. Now through one example we will demonstrate the finite element procedure. So for this we will be taking one simple example of two disk rotor system, which we earlier also we have considered. So this is for demonstrating the procedure. So we have one rotor system like this. Let us say these are the polar mass moment of inertia of the rotor, is supported on frictionless bearing, so it can able to rotate freely on this. This is the length of the shaft, which is massless. The other property of the rotor is this modulus of rigidity and the polar moment of area. This particular problem we can able to solve by assuming a single element like this. This is a single element. We have node 1 and node 2, and corresponding to node 1 we have theta 1 and theta 2 displacement. Now for this particular element we can write the equation of motion. So the finite element elemental equation will be given by, here we are not considering the mass of the shaft, so the mass matrix will be diagonal because the contribution will be coming from the disks only. So here the mass of the shaft has not been considered. Then we have the stiffness matrix, okay, and equal to the internal torque. This is at node 1 and this is at node 2. You can see that our term are nothing but torque, as we already defined earlier. So they are internal torques, and there is no external moment because we are solving the free vibration. So there is no external moment term in this. For simple harmonic motion we can able to write theta double dot as this with minus. So if we substitute in this equation we will get this form of the equation. Then is equal to these torques, let us say T1 and T2. Now we can apply the boundary conditions. Here the shaft is mounted freely on the two bearings. So, both the ends of the bearings, the shaft is free. So, there is no torque at the ends. So, when there is no torque, these both the torques will be 0. So, the equation after applying the boundary condition takes this particular form. And this is a homogeneous equation now, because right hand side term is 0. Now, because this quantity cannot be 0, so we have to have this determinant equal to 0. So, we will see if we put this determinant as 0, this is a n, we will get a polynomial in terms of omega n, and that if we solve it, you will get this form. IP1 plus IP2, and from here you can see that the first natural frequency of the system is 0, and second natural frequency of the system is this. And if we recall, if we substitute this particular quantity as kT is Gj by L, then this particular equation is exactly same as we earlier obtained, either using finite difference method or using the closed form solution. So, in this particular case, even when we consider the approximate solution in the form of polynomial, it gives exact solution. This is a very special case. In other cases like beams, we may not get the similar trend. So, let us take another example in which we will be demonstrating the assembly procedure of the finite element method. For that, we will be taking one small problem in which one cantilever beam will be considered. So, this is a cantilever beam having fixed end. We want to obtain the natural frequency of this particular system. So, for finite element purpose, what we will do, we will divide this particular beam into two elements, 1 and 2. So, we will be having node 1, 2 and 3, and then corresponding displacements are these. Now, we can able to write the finite element equation for element 1 like this. This is the mass matrix, and you can see this for element 1 there are theta 1 and theta 2 as displacements. Similarly, we have stiffness matrix, and these are the angular displacements at node 1 and 2, and they should be equal to the internal torque like this. So, now we will be writing equation of motion for the element 2. In this we have most of the terms for the mass matrix exactly same as the previous element. Only difference will be coming in this vector, where theta 2 and theta 3 are the displacements of the element 2. Then stiffness matrix remain the same, only difference will be coming in this 2 and theta 3 vector is equal to the internal torque Now we can combine the element 1 and element 2. I am showing the procedure for this assembly procedure. So here first I am entering the mass matrix for both the elements. So first element is contributing here, for second element will be coming here, and rest of the elements are 0. So this is the assembly. This blue color represent that element 2 and black color represent element 1 contribution. Similarly, we can able to assemble the stiffness matrix like this: theta 1, theta 2, theta 3, and contribution from the first element will be this, and for the second element will be having contribution here. Rest of the terms are 0. For force factor we have minus T1, T2 is coming from the second element. So here you can see that this term is getting 0, and because here one end of the beam is fixed, that means at node 1 it is fixed. So there the displacement will be 0, and other end of the beam which is free end, that is a cantilever, so their torque will be 0. So those boundary conditions will be applying in this. So this becomes 0, then T3 is 0 because that is a free end, and in the previous slide theta 1 is 0, that is a mass matrix. So you can see that in this particular case finally we will be left with 2 by 2 matrix, because we need to eliminate the first row and first column because they are getting multiplied by 0. So we will be left with this particular terms, and in the similarly in the stiffness matrix we will be left with this particular term. So after applying the boundary condition, our equation of motion is reduced to 2 by 2 size of this form. This is coming from the mass matrix. Let us go back to the previous slide. This 2 into 2, 4, and here we have only 2 vectors, this one plus stiffness term theta 2, theta 3, okay, and right hand side both are 0. Now for simple harmonic motion we know that we can able to write the theta in terms of theta double dot in terms of omega square and theta. So we will be having for simple harmonic motion, because we are analyzing the free vibration where this is the natural frequency. So previous equation reduced to, we can able to club in a matrix form. this is first term, then second term. In this, both the mass matrix and the stiffness matrix has been clubbed in one place. And the last term is this, and it is getting multiplied by theta 2 and theta 3, and that is equal to 0. So, that is homogeneous equation, because this will go here. This is a homogeneous equation, and for this because we cannot have the trivial solution, that means both the displacement theta 2 and theta 3 cannot be 0. So, the determinant of this particular matrix has to be 0, and from there we will get a frequency equation in terms of omega, and I am writing the final form of the matrix. A and B I have defined some parameter. I will be defining this. Where A is Gj by H and B is rho j H by 6. So, we can able to solve this for omega n. This will give us two natural frequency of the system. First one is this, second is and because earlier we have already obtained the closed form solution for the cantilever case. So, let us see those expressions directly. That is a closed form solution. This is the closed form solution for cantilever beam case. So, n can be 1, 3, 5 various modes they represent. So, for omega 1 exact solution is 1.5708 and this quantity, and omega n2 is 4.72 g rho L square. So, if we compare with our result is 1.6, which is close to 1.57, and this is 5.63, which is slightly away from the 4.72 for the closed form solution. Here one aspect is there, we have considered only two element for demonstration purpose, but we can able to increase the number of element if we are writing a program, computer program for this particular problem, in which we can able to increase maybe 3 element or 6 element or 10, or maybe we can go up to 100 element, and we will see that as we will increase the number of element, our results will be closer to the exact solution. That is generally we perform for the finding out the convergence criteria, means what should be the number of element we should have so that we are close to the exact solution. Now we will be developing elemental equation for gear element. We have already analyzed the gear through the previous transfer matrix method, also by the direct method. Let us develop the elemental mass matrix and the stiffness matrix for the gear element. Then through one example we will demonstrate the procedure of finite element method. Let us take a gear like this. This is a rotor, let us say a P1, this is a gear, this is another gear, and is connected to shaft through to another rotor let us say this is IP3. Now the displacements of the gears are G12 and theta G1 and theta G2. Now let us draw the gears separately. This gear 1 and this gear 2, and let us say it is rotating with omega 1, and then the gear 2 will be rotating with omega 2, and they are related with the gear ratio, that is omega 1 divided by omega 2. Now in finite element method, generally the convention is to represent the displacements in the same directions. So for two gears we are writing these are the torsional displacements. Gear is rotating at some RPM, but it is getting torsional vibration because it is transmitting power. Now we have taken these directions same because in finite element method there is the convention. So the relationship between these two displacements will be like this. Minus sign is because in the figure they are in the same direction, but should be in the opposite direction for actual case. Now from the previous the analysis, we know that if we want to do the equivalent system for this gear element, we have to divide the especially the polar mass moment of inertia by the gear ratio square. So that will give us what is the inertia force which we will be getting in terms of the gear displacement 1. So here we have obtained the equivalence of the polar moment of inertia of gear 2 because theta G1 and theta G2 are related. So we want to eliminate the theta G2 from the equation. Now let us write the elemental equation for the stiffness. So for that let us take the shaft having stiffness K1 and is having element node 1 and node 2, and correspondingly theta 1 and theta 2 are the displacements, and this theta 1 is actually the gear 2 displacement, because this particular shaft which we have chosen in previous figure is this particular shaft. So this end is element node 1, node 2, but this particular displacement is assigned to node 1. So that is why we are calling this as theta G2 is equal to, we know that is theta G1 by n. Now let us write the strain energy due to this, that will be K1 theta 2 minus theta 1 whole square. This is the relative twist between the two ends of the shaft. So this is the strain energy. We can substitute for theta 1, that is theta G1 by n whole square. Now work done is given as T1 and T2 are the reaction torques at node 1 and 2. Again we can able to replace theta 1, so we will be getting theta G1 by n minus T2 theta 2. Now we can able to use Lagrangian equation to obtain the equation of motion. So, for Lagrangian equation we need to differentiate the strain energy plus the work done by the variables which we have, that is theta g1 and theta 2. So, we will get theta g1 by n plus theta 2 is equal to minus t1 by n, and this second term will be getting theta g1 by n plus theta 2 is equal to t2. Now, these two equations can be combined in a matrix form like this, in which first term is theta g1, another is theta 2. So, here you can see that we have eliminated the actual displacement of gear 2, that means theta g2 by theta g1, because they are related. So, this equation will take form of this form, minus t1 n by second term is t2. This particular equation is the stiffness matrix, which we need to consider for the analysis of the gear element, and we have already seen the change in the mass matrix will be this much. So, now we will be taking one example of the branch system in which one shaft is giving power to two shafts, and using finite element method, which we already developed the elemental equation for stiffness and mass matrix, will be demonstrating the procedure. So, in this particular problem we have one rotor which is connected through shaft to a gear. Let us say this rotor is A, this is gear is B, this gear is connected to gear C, and that itself is connected to another rotor E, another disc I should say, and this again there is another gear, that is D, and this is another rotor disc, that is F. Okay. Various parameter of these are like polar mass moment of inertia of the disc A is 0.01 kg meter square, of disc E is 0.005 kg meter square, and of disc F is again 0.006 kg meter square. Diameter of various shafts are this 0.2 meter diameter, is having 0.1 meter diameter, is having 0.4 meter diameter. Lengths, for simplicity we have taken as 1 meter, all the lengths are 1 meter of the all three shafts. So, these are the various dimensions of the various shafts. Gear ratio between B and C is 3, and gear ratio between B and D is 4, and modulus of rigidity again is this much. So, these are the parameters of the branch system. This is a branch system in which power is coming from one shaft and going to two shafts. So once we have given all the parameter of the shaft, now we will be dividing this three shaft system to three elements, and we will be writing the elemental equation for each of this, and then we will be assembling the elemental equation, and we will be applying the boundary condition, and finally then we will be getting the natural frequency of the system. So let us do it. So this is element 1. Element 1 is in which we have theta A, theta B, and IP A, IP B. In this I forgot to give the IPB value, that is 0.005 kg meter square. I will be giving other gear polar mass moment of inertia also, as I will be going to respective elements. So the elemental equation will take this form. This is the first element. K1 is the stiffness of element 1, and these are the torques, internal torques. Similarly, for element 2, we can able to, here we have theta B, and here we have theta E. Theta C is related with theta B by gear ratio BC. So we could able to eliminate theta C from this element. So elemental equation will be IPC BC square 0 . Here theta B double dot is there, that's why we have to divide by the gear ratio. Then the stiffness matrix also will get changed. We have to divide by gear ratio square for first term. For second term, as it is, only NBC we have to divide. Here also we have to divide by NBC. This remain as it is. Theta B, theta E, and right hand side is theta C by NBC and theta E transpose. Element 3 is having one side theta B again, because we have related the displacement of disk D with B, that is D is related with B through BD, gear ratio BD. Here it is F. So the elemental equation for this is Now we have obtained all the elemental equations. Now we can able to assemble them. So this equation also will be showing the final, I think. This equation will be showing at the final, no? Okay. There is no need to show the writing part. Now after assembly, the equation will take this following form. Now here you can see that we have 4 displacements, that is at node A, B, E, D only. Now we can apply the boundary condition here, and especially you can see that this particular term of the torque get cancelled totally, because when we assemble the matrices, those torques they cancel each other. Now if we apply the boundary condition, we have boundary condition that the end A is free, so this torque will be 0, and E is also free, so this is 0, and F is also free, so all these torques are 0. We will go back to the, here you can see this, and E is free and F is free also, and A is free, so torques will be 0 at these ends. Now we can able to write the previous equation in this particular standard form. And in this right hand side terms are 0. The size of this matrix is 4 by 4 into 4 into 1. Now for simple harmonic motion, we can write this as, so the equation becomes and from here if we take the determinant of this quantity 0, will get a polynomial in terms of omega n, and if we solve these polynomial, we will get 3 roots of the omega n. First will be 0, first is 0 because this is free end, second will be 1.16 10⁻⁶ radians per second, third natural frequency would be 5.09 10⁻⁶ radian per second, and fourth natural frequency would be 21.5 10⁻⁶ radians per second. Because in this particular case we had 4 disks, so we got 4 natural frequency of the system. For this particular example we had 4 disks, so because of that we got 4 natural frequency of the system, and because ends of the shafts were free, so we got 1 natural frequency as 0, which is corresponding to the rigid body mode of the vibration. So today we saw the finite element analysis of the torsional vibration of rods. We developed the elemental equation for mass and stiffness matrix for a continuous system, and then we demonstrated the finite element procedure, even the assembly procedure, using examples. Then we took the gear element stiffness and mass matrix development, and that also we demonstrated through example. With these examples, I think all the concepts are clear to you.